Somewhere 1,300 light-years from Earth, there's a star that looks, at first glance, almost exactly like our own Sun. Same basic type, same general age range, nothing unusual until you actually look closely at its chemistry. Buried in that star's light is evidence of something it shouldn't be possible to witness directly. Astronomers think this star recently ate one of its own planets, not metaphorically. A real, rocky world, pulled in and consumed, leaving behind a chemical scar that scientists only just learned how to read. The star is called TOI 5882, and the discovery comes from a team led by Brooke Kotten, a graduate student researcher in the Department of Astronomy at the University of Michigan, with senior author Melinda Soares-Furtado, an assistant professor at the University of Wisconsin. Their findings were published in the Astrophysical Journal. Here's the problem astronomers usually run into when they want to study something like this. A star swallowing a planet is an extraordinarily fast event on cosmic timescales, often taking only days or weeks from start to finish. Compared to the millions or billions of years most astronomical processes unfold over. That's essentially instantaneous, the astronomical equivalent of trying to photograph a single blink in the middle of a decade-long exposure. Nobody has ever caught one of these events actually happening in real time. And given how briefly they last relative to a star's entire multi-billion-year lifespan, it's reasonable to assume nobody ever will directly. Instead, scientists have to go looking for the aftermath, chemical fingerprints left behind in a star's atmosphere, long after the planet itself is gone. The only kind of evidence that actually lasts long enough to still be there when someone finally points a telescope at the right star. The fingerprint in this case is lithium. TOI 5882 has an unusually high concentration of lithium in its outer layers. And that detail matters far more than it might sound like it should, because of exactly where the star is in its own life cycle. TOI 5882 is classified as a subgiant, a star that has finished the main hydrogen-burning phase of its life and started expanding, on its way toward eventually becoming a full red giant. Our own Sun will eventually pass through this exact same subgiant phase itself, billions of years from now, before it too swells dramatically in size. Stars at this stage are expected to have less surface lithium than younger stars, not more. As a star ages, its outer layers deepen and mix with hotter material from further inside. And lithium is a notably fragile element, easily destroyed once it's exposed to those hotter conditions. A subgiant star with a normal, uneventful history should be gradually losing whatever lithium it started with, not accumulating an unusual surplus of it from somewhere else. To confirm just how unusual TOI 5882's lithium level actually was, the team didn't rely on a single measurement in isolation, which on its own could easily be misleading. Using spectroscopy, a technique that splits a star's light into its component wavelengths to identify the specific chemical elements present, essentially reading the star's own fingerprint out of the light it emits, they compared TOI 5882 against a carefully matched control group of 62 other stars, selected specifically because they shared similar ages, masses, and temperatures. Matching the comparison stars this closely matters, because lithium levels naturally vary somewhat between stars for entirely ordinary reasons. Without a fair, like-for-like comparison, an unusual reading could just as easily be dismissed as normal variation. Against that carefully built comparison group, TOI 5882's lithium levels placed it at least in the 97th percentile. Soares-Furtado noted that no matter how the data gets analyzed, the signal holds up as genuinely unusual. not a statistical fluke or a result of cherry-picking the comparison. So where does the extra lithium actually come from? The leading explanation is straightforward, if violent. Rocky planetary material is far richer in lithium than a star's own outer layers naturally are. Since planets never went through the same fusion processes that gradually deplete lithium inside a star. If a planet spirals into its star and gets consumed, the lithium from that planet gets mixed into the star's atmosphere, temporarily spiking the concentration to a level well above what the star would show on its own, given its age and evolutionary stage. Based on how much excess lithium is present, the team estimated the swallowed object was likely somewhere between a few times the mass of Earth and the mass of Neptune, a real planet, not a stray asteroid or comet, and roughly the same size range as several of the rocky and ice giant worlds already familiar from our own solar system. There's still an open question about how the planet ended up on a collision course with its own star in the first place. The system contains a massive brown dwarf companion, and the research team believes its gravity may have played a role, dynamically disturbing the orbit of the doomed planet over time, until its path finally bent inward toward the star itself. A brown dwarf sits in an odd middle category of object, more massive than a planet, but not quite massive enough to sustain the nuclear fusion that defines a true star. Essentially a failed star that never quite reached ignition. Even without becoming a star itself, its gravity was apparently enough, over some long stretch of time, to help destabilize an entire planetary system orbiting nearby, nudging one unlucky planet's orbit until it had nowhere left to go but straight into TOI 5882 itself. Kotten summarized the underlying idea about as simply as it can be put. You are what you eat. A star that consumes a planet doesn't just destroy the evidence completely, the way you might expect an object that hot and massive to. It also quietly absorbs a chemical record of exactly what it consumed, written into its own atmosphere for astronomers to eventually find, if they know precisely what unusual signature to look for. There's a broader implication buried in this discovery that goes beyond one distant star. If planetary engulfment leaves a detectable, lasting chemical signature like this, astronomers now have a genuine, practical method for hunting through existing archives of stellar data and future surveys to identify other likely engulfment events that nobody has previously flagged, essentially retroactively searching for a crime scene that was never recognized as one at the time. Interestingly, a handful of other stars in TOI 5882's own comparison sample also showed somewhat elevated lithium levels, hinting that this kind of violent planetary loss might be considerably more common across the galaxy than astronomers have generally assumed, rather than being the rare, freak occurrence it might initially sound like. That question matters for a reason closer to home than 1,300 light-years. As stars age and evolve, their gravity and physical size both shift substantially. And that process is exactly what can destabilize the planets already orbiting them. Studying a star like TOI 5882 offers a real, physical preview of a fate that isn't unique to distant, unrelated star systems. Every planetary system built around a sun-like star, including our own, is on the same basic evolutionary track, just at an earlier point along it. Our sun is currently a stable, main-sequence star, but it will eventually become a subgiant too, then a red giant, expanding outward in ways that could threaten the very innermost planets of our own solar system, long after humanity is gone to witness it. TOI 5882 wasn't caught in the act. Nobody watched the actual collision happen, because nobody could have, given how fast and how far away it was. But the star kept the receipt anyway, written directly into its own atmosphere. For anyone with the right instrument, the right comparison sample, and the right question, to eventually go looking for it, a permanent chemical record of a planet's final moments, hiding in plain sight inside the light of an otherwise perfectly ordinary-looking star. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel, new episodes on space, physics, and the edges of what we understand, going up every day.